Am I audible? हेलो।
यस सर।
चलो ठीक है, स्टार्ट करते हैं। सो इन लास्ट
एक्सक्यूज
क्लास।
मी सर।
हाँ बोलो।
सर वो लास्ट लेक्चर में जो डिकैंटर वाला था
हाँ
उसमें ये जो ZA2 वाला जो मतलब वो ओवरफ्लो क्या है, मतलब ये नीचे वाले पॉइंट पे सर जहाँ से वो निकल रहा है, एंड देन सर वो ओवरफ्लो प्रिंसिपल क्या है, मतलब कि वो एटमॉस वहां और वहां का प्रेशर हमने इक्वेट क्यों कर दिया?
देखो, बेसिकली इन द डिकेंटर इसमें क्या हो रहा है कि आपके दो फ्लूइड, एक मिक्सचर है फ्लूइड का, है ना, जिसके अंदर दो इमिसिबल फ्लूइड है, वो फ्लो इसके अंदर फीड किया है, और देन इट मेक द टू लेयर्स, है ना। तो जो अपर लेयर है उसके अंदर लाइट फ्लूइड आ गया, जो लोअर जो हैवी लेयर है वो नीचे बॉटम में आ गई। अब ये दोनों कंटिन्यूअसली इससे बाहर आ रहे हैं। तो अब आपको ये देखना है डिजाइन इक्वेशन में कि कहां पर इनका इंटरफेस होगा, क्योंकि अगर ये इंटरफेस जो है दैट इज द ZA1, अगर ZA1 की वैल्यू जो है वो अपर प्लेट के ऊपर चली गई, तो फिर आपका जो अपर प्लेट है, जो अपर जो ओपनिंग है, वहां से भी आपका हैवी फ्लूइड आने लगेगा, है ना। और अगर ZA1 की वैल्यू बहुत कम हो गई, तो जो बॉटम आपका पाइपलाइन है वहां से भी आपका जो लाइट फ्लूइड है वो आने लगेगा। तो होता क्या है कि बहुत अगर आपने यहाँ पर एक ZA2 नहीं दिया, है ना, इफ यू हैव नॉट गिवन दिस ZA2, तो क्या होगा कि ऑल द फ्लूइड्स विल कम फ्रॉम द बॉटम प्लेट ओनली, है ना। सपोज हियर यू हैव ओनली वन होल, सपोज here you have only one hole, है ना, इस तरह से एक होल है इसमें। then what will happen, all fluids comes from the this hole only, है ना, because here you have the, due to the overall weight of the fluid will come from this hole only. Okay, so what we have done, instead of giving the simple hole, we make a head, है ना। तो यहाँ पर एक हेड बना दिया हमने। तो just pipeline goes from bottom of the tank, then it goes to the upper direction. Okay, and in fluid mechanics always remember, whenever the pipe is open to the atmosphere, है ना, जब भी पाइप एटमॉस्फेयर में ओपन होता है, तो द प्रेशर एट द एटमॉस्फेयर इज 1 atm, है ना। सो हियर द प्रेशर इज 1 atm, हियर द प्रेशर इज 1 atm। ओके, एंड फ्लूइड्स कम्स आउट डायरेक्टली, है ना, ड्यू टू द वेट ऑफ द फ्लूइड इनसाइड द टैंक, है ना। बेसिकली ड्यू टू द वेट ऑफ द फ्लूइड इनसाइड द टैंक, फ्लूइड इज फ्लोइंग फ्रॉम द पाइपलाइन, है ना। तो इसको ऐसे समझ सकते हो कि अमाउंट ऑफ फ्लूइड्स कम्स आउट, जो यहाँ पर इसको फोर्स लग रहा है फ्लूइड को बाहर आने के लिए, सपोज यहाँ आपका फोर्स F1 लग रहा है, यहाँ पर आपको फोर्स F2 लग रहा है, जो फोर्स है जिससे फ्लूइड बाहर फ्लो कर रहा है, दैट शुड बी इक्वल टू द pressure generated by the fluid inside the tank, है ना। तो we are equating the this pressure, the how much force is available here, है ना, that should be equal to the pressure generated by the tank. So when you equate the both force, you know that the where is the interface line, है ना, because the crucial design part is the interface should not be greater than the upper hole, है ना. If the interface is greater than upper hole, then your water will comes from the upper tank. ठीक है. Otherwise, if the pressure is, if the interface is very low, then your water will, then the oil will come from the bottom plate. And generally this type of decanter are used to separate out the oil water mixture. Okay, so you have to design the system in such a way that interface of the oil water mixture should lie in between these two holes. So you will get the oil from the upper hole and the water from the bottom hole. समझ में आया अब?
Yes, sir. Thank you.
ठीक है. Now this is the design equation. After the derivation, we get the design equation. The interface should be equal to ZA2 minus ZT, rho B divided by rho A divided by 1 minus rho B by rho A. So this is the final equation. Now the time of separation. How to calculate the time of separation? है ना. So there is an empirical correlation to calculate the time of separation. Okay. So the time of separation T can be calculated as, this is the empirical equation. There is no theory behind this. This is the empirical equation. Rho A minus rho B, where T is the separation time, in hours. Rho A and rho B are the densities of liquids A and B in kg per meter cube, and mu is the viscosity in centipoise. Mu is the viscosity of continuous phase. So viscosity of continuous phase means viscosity of the fluid which is feeding inside the tank and inside the decanter. So before entering the decanter, the mixture has some viscosity. So the viscosity of that mixture. So this is a empirical correlation. This comes out by the experiment, this correlation. There is no theory behind this equation. Okay, so you have to just remember this equation. In centipoise. Okay, so these are the correlation for calculating the time required for separation. Okay, so once you know the time required for separation, you can also calculate the size of the decanter, how much big decanter you required for separation. Okay, now second type of decanter which we can use is the centrifugal decanter. So we have studied the hydrostatical equilibrium as well as the hydrostatical equilibrium due to the pressure force, due to the standing fluid, and second is the hydrostatical equilibrium due to the centrifugal force. So the centrifugal force can also be used to separate it out the two different types of liquids. So we will discuss the derivation for that. Centrifugal decanter.
सर पिछले फॉर्मूले में सर म्यू किसके लिए होगा सर? वो
म्यू विस्कोसिटी,
वो फिर एंड ये कंटीन्यूअस किसके लिए होगा सर? ये कंटीन्यूअस
फेज मींस द मिक्सचर व्हिच यू आर फीडिंग, है ना. सो यहाँ पर जो आपका फीड आ रहा है दैट इज द मिक्सचर ऑफ ए एंड बी. सो इसकी विस्कोसिटी है ये.
Okay, sir.
Okay, and now here you have the A. Here the A and B are separated out. Lekin the time required depends upon the actual viscosity of A and B mixture which you are feeding inside the tank. And initially it comes out like a emulsion solution. And so you are separating out the emulsion solution in the two different fluids. Okay,
Okay, sir.
so the original emulsion solution has the viscosity mu. Okay,
Okay.
now we will discuss about the centrifugal decanter. This is the basic diagram of the decanter, how it looks like. So basically you are feeding the two fluids, mixture of two fluids in the decanter. Okay, so here you have one fluid which is the lighter fluid. And then you have the heavier fluid which goes to the near to the wall, है ना? So basically there is a central tube between the, so the centrifugal decanter contains a cylindrical type of structure, and you have a centrifuge, you have a cylindrical type of structure which can be rotate in the angular motion, with the angular motion, and you have a central tube inside this tank, center of the tank. So this is the central tube. The mixture of the fluid is entering from this tube at the bottom of the decanter. Okay, so mixture hota hai, that will be fed at a bottom of the decanter by using this tube. Okay, and because this system is moving very fast, this system is rotating very fast at very high speed. So this is the system, it is rotating it with very high speed omega. So what will happen due to the movement, as the fluid enters in this decanter, it moves towards the wall. Okay, and the lighter fluid comes out as a outer layer, and the heavier fluids goes to the inner layer. Okay, so you have the separator, you have the outlet at the top of the column, which is the overflow point. And here also fluid is coming out due to the overflow. And so it just make it to wall. And so this is the vertical walls. Okay, because the rotational speed of the decanter is so high, it is like 400 rpm per minute or the 5,500 rpm per minute. So at this speed, fluid will not remain in the conical. If you are rotating the cylinder at a lower speed, you will find a conical eddy type of structure. But if you increase the speed, then you will get a parallel perpendicular walls. Okay, and due to the overflow, fluid comes out from these 2 points. Okay, so here you will get the heavier fluid, here you will get the lighter fluid. So this is also a continuous system. This is also a continuous system, and this system you will find in the industry a lot. And whenever you want to separate out the two fluids, and similar type of structure is also used, similar type of unit is also used to drying the sugar. If you if you visit any sugar mill, you will find similar type of structure to dry the sugars. Okay, so they remove the water from sugars by using this type of centrifuge. Okay, so basically the fluids comes out due to the overflow only, similar to the continuous decanter. And the radius is given as, so this radius is from here to here. Okay, so this is the radius where the fluids comes, the lighter fluids comes out. So that is the RB, small rb. The heavier fluids comes out from this point. This is the RA, and the interface situated at the point RI. Okay, so RI represent the interface. RA is the radius of the overflow point for the heavier fluid, and the RB is the radius of the overflow point for the lighter fluid. Okay, now what we will do, because fluid is coming out due to only due to the overflow, the pressure difference between both points should be equal. Okay, so in this case, first I will write the notations. Suppose heavier fluid have density rho A. Which overflows at the radius RA. Similarly, lighter fluid has density rho B, which overflows at radius RB. Okay, now the interface between the two separating fluids are present at radius Ri. at radius Ri. Okay, so because fluid is not moving, है ना, whole system is moving, but fluid is not separately moving, है ना. If you compare the velocity of these two fluids, so they are same. So basically, the whole system are moving as a one body, as a solid body, है ना. So whenever you use the centrifuge, the fluid is not moving separately, है ना. Fluid is moving with the system only, with the unit, whole unit only. So it looks like as a solid body, and not a simple flowing system. Okay, so it is like the solid body. So that is only possible when the pressure difference between these two points are equal. And this is only possible when the pressure difference in the light liquid between R. This is only possible. Hydrostatic equilibrium is only possible when pressure difference between outlet radius जो आउटलेट रेडियस पे जो प्रेशर है, यहां पर जो प्रेशर आ रहा है इस पॉइंट के ऊपर, इस पॉइंट के ऊपर और इस पॉइंट के ऊपर, द प्रेशर डिफरेंस बिटवीन आउटलेट रेडियस एंड इंटरफेस आर equal. Okay, then only you have the hydrostatic equilibrium, otherwise fluid will start to move. Okay, so if you are moving the, if you are rotating the centrifuge at very high speed, then you will achieve the hydrostatic equilibrium, then fluid will stop to move. It looks like a solid body, due to the force, and at that time the liquid will be separated out, both liquid will be separated out, and the pressure difference between the points are equal. Okay, so you can write Pi minus Pb, these are the pressures, not density, that is equal to Pi minus Pa. Okay, where Pi is the pressure at interface Pb is the pressure at the free surface of fluid. Pb is the pressure at free surface of light liquid, at the free surface of lighter liquid Rb, and Pa is the pressure at the free surface of heavier liquid at RB है ना, heavier liquid at RA. Okay, now you remember the hydrostatic equilibrium when you have the centrifugal force. So for the equation of hydrostatic equilibrium due to centrifugal force, from the equation of hydrostatic equilibrium, due to centrifugal force you will have Pi minus Pb Pi minus Pb, that should be equal to omega square. Omega is the angular velocity, omega square rho b is the density, multiplied by difference in the radius, Ri square minus Rb square divided by 2. Okay, now there is the GC. GC is a coefficient. The value of GC is 32 and it is used when you are solving in the FPS unit. And if you are not solving in the FPS unit, you are solving in the SI unit, the value of GC equal to 1. Okay, so I am using the GC because in the some examples, some numericals, we will use the FPS unit and a British unit. So whenever you use the British unit, you will use the GC. Okay, otherwise GC will be 1. Okay, now similarly for the other fluid, you can write Pi minus Pa, that is equal to omega square rho A Ri square minus Ra square divided by 2GC. Okay, both you have to equivalent the both equation. So from both equation we will get, so these two equations represented that rho b Ri square minus Rb square equal to rho A Ri square minus Ra square. Okay, now from this equation you can determine the value of Ri. So when you solve this equation, you will get the Ri. So Ri equal to root of Ra square minus rho b divided by rho A Rb square divided by 1 minus Rb divided by Ra. So this is the interface in the centrifuge, in the continuous centrifugal decanter. Okay, so this is the final equation for centrifugal decanter. Okay. Now we will solve some numerical also. So first numerical is related to the YouTube manometer. So this is also given as an example in the MACAP book. So I am giving you the same numerical. So a manometer a YouTube manometer है ना, precisely YouTube manometer, not the manometer. A YouTube manometer is used to measure the pressure drop across an orifice the pressure drop across an orifice. Orifice is the equipment which is used to calculate the flow rate, है ना? So that is written in the orifice. Liquid A is mercury. So barometric fluid is mercury. Liquid A is mercury. With the density R rho A equal to 13,590 kg per meter cube. This is the density of mercury at the room temperature. Okay. Now fluid B flowing through the orifice is brine. Fluid B is brine. Fluid B flowing through the orifice is brine having density rho B. So this is the second fluid. Rho B equal to 1260 kg per meter cube. Now when the pressure of the taps are equal, when the pressure of the tapes are equal, the level of mercury in manometer is 0.9 meter below of the orifice tap. The level of mercury in the manometer is 0.9 meter below the orifice tap. Okay. Under operating condition, gauge pressure at upstream is 0.14 bar. Under operating condition, the gauge pressure means above atmospheric pressure, the pressure which is measured by the gauge pressure at upstream is 0.14 bar, and downstream is 25 mmSg below atmosphere, and downstream is 250 mmHg below atmosphere. Now what is the below atmosphere means? It is in vacuum. Downstream reading is in vacuum. Okay. So what is the reading of manometer? What is the reading of manometer? तो मैनोमीटर की रीडिंग बतानी है आपको, है ना. So here the pressure drop is given upstream. What is the meaning of upstream and downstream? Suppose there is a process, so the stream or the flow which is entering in the process, that is called the upstream. Okay, and the flow which is leaving from the process, that is called the downstream. Okay, so at the upstream you have the pressure 0.14 bar above atmospheric pressure, and downstream you have the vacuum, that is the 250 mmSg below atmosphere. This is the above atmosphere, this is the below atmosphere. Okay, so you because it is given in the atmospheric terms, so we can take the atmosphere gauge pressure only. It is easy to calculate the gauge pressure in these conditions. Okay, so what is the first we will calculate the pressure, then only we can calculate the pressure drop. Okay, so first thing, solution. In the solution, first you have to calculate the pressure in the single unit. Here one unit is in bar, one unit is in mmHg. So I am calculating the pressure in terms of Pascal in gauge pressure. Okay, so everything will be written in the gauge pressure. Okay, so upstream pressure is that is equal to 0.14 bar multiplied by 10 to the power 5, it will become the Pascal. Okay, so it will become the 1400 Pascal, 14,000 Pascal in the gauge, because it is already the gauge pressure. Now the downstream pressure is downstream pressure is 250 mmHg below atmosphere. So 1 atmosphere pressure is the zero gauge pressure. So I can use the negative pressure here, है ना? If 1 atmosphere is the zero gauge, 1 atm equal to zero gauge. So this is the below atmosphere, so it will goes in the negative direction. Okay, So what? How to calculate the mmHg? First, you to convert the mm into meter. So that is equal to 250 divided by 1000. It will convert mm into meter. Multiply by gravity. Gravity is 9.8. Multiply by density. Density is 13,590 for the mercury. So when you calculate this quantity, it will become the, and it should be the negative because it is the below atmosphere. So it will goes in the negative direction. So it will come out as a minus 33,318 Pascal. So now it will be in the SI unit. Okay. Now both units are same. Okay. So difference is delta P equal to PA minus PB. This is the PB. So delta P equal to PA minus PB. So PA is the 14,000 Pascal. PB is the minus 33,318 Pascal. So when you take the difference between the two units, you will get the final answer. कितना आएगा बताओ? 47318 Pascal. This is the pressure difference. Okay. Now, once you know the pressure difference, so delta P equal to RM. RM is the reading, manometer reading, multiply by G, multiply by rho A minus rho B. This is the formula for manometer, YouTube manometer. Delta P is known, rho A is known, rho B is known. It is given in the equation, in the problem. Okay, so what are the values? Delta P is 47,318. That is equal to RM multiply by 9.8 multiply by density rho A minus rho B. So what is the value of rho A? That is the 13,590 kg per meter cube. 13,590 kg per meter cube minus rho B is the brine, and the density of brine is given as 1,260 kg per meter cube. When you solve this expression, you will get the value of RM. So RM will come as a 0.391 meter, or in the mm, it will equal to the 391 mm. This is the difference between the U-tube. And so basically this is the U-tube. So what is the difference between the level of U-tube? And so suppose the mercury is filled up to this point. Here mercury is filled up to this point. So the actual difference from here to here is, that is difference, that is the 391 mm for this problem. Okay. So this is the solution of the U-tube manometer. In next class, we will solve some problem related to the continuous decanter. Okay. Then I will give you a assignment which is related to the problem related to the manometer as well as the continuous decanter. Okay, I think this is enough for today's class. ठीक है?
ओके सर।
ओके सर।
चलो फिर नेक्स्ट क्लास में मिलते हैं नेक्स्ट वीक।
ठीक है सर।
ओके सर,
थैंक यू सर।
चलो ठीक है,
थैंक यू सर।
ओके।